Okay, welcome back everyone. So I'm looking forward to continuing the lectures that we started yesterday on dark matter. I'm changing the order slightly relative to the program. I want to start out this lecture by finishing what we were discussing yesterday about the cosmology of cold dark matter axions. So I told you yesterday about axions are motivated from the strong CP problem, from considerations of wanting the axion to be stable. That tells you that it has to be lighter than about 20 eV. If you go higher than that, it tends to decay faster in the lifetime of the universe because heavier axions couple more strongly to the standard model. So as we push to lower and lower masses, the couplings become smaller and smaller. Because the axion's that light, it would be hot dark matter if it thermalized with the standard model. So we need to require that it's weakly coupled enough that it doesn't thermalize appreciably. And that pushes us to the milli-eV and below scale. So now I want to talk about, okay, let's suppose we're in this situation. We have this very light, so milli-eV and lower, all the way down to the 10 to the minus 21 eV level that we talked about earlier. Very light, very weakly coupled, non-thermal, cold, bosonic, dark matter. As we discussed yesterday, it can't be a fermion. What happens to the cosmology in that case, and why does something like this even necessarily act like cold dark matter to begin with? So we'll see how that works. Then I want to spend some time talking about current searches for axions and other ultralight axion-like particles. This is inevitably going to be kind of a sketch of the field because I don't have infinite time and it's quite possible to give a whole series of lectures just on axions. And then I want to ideally go on and talk about other Earth-based strategies for looking for dark matter candidates in direct detection at colliders. Again, these will be outlines. I will provide references to more detailed reviews that people can dig into if they like. And then in the second lecture today, I'm going to talk about the indirect detection searches, which are so astrophysical and cosmological searches, and using that to try to constrain dark matter. It's my particular area of interest. Okay, so continuing, so yeah, this is the recap from last time. We talked about thermal WIMPs up at higher scales, where the dark matter could get its abundance through interactions with standard model particles in the early universe. We talked a bit about how this thermal window worked. But in general, dark matter could inhabit an enormous range of mass scales, and there are many orders of magnitude and possible mass range where the dark matter has to be cold, non-thermal, bosonic, and the axion is the sort of classic example of dark matter that's like that. So I'm telling you about the QCD axion, but people often talk about axion-like particles generally, which again are very light, ultra-cold, very weakly coupled bosons. Okay, so for the axion, how does it get its abundance? So when we're talking about sufficiently cold and sufficiently light particles, the large occupation number, we can really just treat this as a coherent classical field that's evolving in an expanding universe and ask how the energy density stored in that field will evolve. So the stable minimum energy configuration is that the field is at the bottom of a potential. But if you started out somewhere not at the bottom of the potential, then, so misaligned, we say, by some value from the minimum, then it will roll down this potential, roll back and forward, and the question is, what does its energy density look like, and how does it behave while it's in this oscillating phase? So, okay, so if we want to actually calculate this, we can write down the equations of motion. We derive this from the Lagrangian coupled to the action for the expansion of the universe. And what we get is something that looks schematically similar to the Boltzmann equation that we had last time. We have a kinetic energy term from the acceleration of the okay, sorry. This is just a typo. This is meant to be a second derivative. I don't know how I did that. That's a late night typo. There's a second derivative, and then there's this first derivative term that is associated with the expansion of the universe. I'll fix this on the slides before I post them to you. And then we have a term that comes from the potential. So when we expand the minimum around the potential around its minimum, as we said last time, we get a quadratic term whose coefficient is the axion mass. Close to the minimum of the potential, we can approximate it as quadratic. So we can solve this equation of motion, where this is the second derivative. And we can just solve this numerically, but we can think about some different limits where we can understand the solution analytically. So the first is, if I'm in the limit where if I set this mass to 0, this differential equation has a very simple solution, which is that d by dt of this axion field is 0. Okay? That's a valid solution. there are other, so in this regime we say that the field is frozen. It just doesn't evolve. However, once the mass of the axion starts to become comparable to Hubble, then the field starts, so now imagine that I can take the opposite limit where this term, this expansion term, is pretty negligible compared to the other two terms in the equation. So then this is just an oscillatory, solution. We have a, you can think of this as like a simple harmonic oscillator with a Hubble-dependent friction term. So that means that our solution is going to have some cos MAT or sin MAT dependence. You can read off just from that. And then there'll be some overall scaling with a slow dependence on the time that comes from this Hubble friction term. So we can write the solution once it begins to oscillate as an initial condition times a slowly varying f of t term times this fast oscillation. We can then solve for this f of t term. If you do that, if you take the sort of next order so the leading order terms, these two give you the cos MA of t term. If you take the next order terms, when you expand this equation, you get an equation that looks like this for f of t. That could be simplified just down to this differential equation. So that tells you that f scales like the scale factor a to the minus 3/2. So we have so once the field starts to oscillate, its amplitude is slowly being depressed by the expansion of the universe, and in addition to that, it has this fast oscillation. So how much energy density is stored in this field? Well, it has a kinetic energy component, which is half a dot squared, and it has a potential energy component, which again, if we're oscillating around the base of the potential is basically just quadratic. The shape of the potential term is entirely set by the axion mass. So we can just write it like this. We can plug in that solution ansatz that we wrote down before. We see, as you would expect in a harmonic oscillator, these fast oscillatory terms from the kinetic energy and the potential energy cancel out. This is just like a pendulum swinging back and forward. It's transferring kinetic energy to potential energy and vice versa. So then we end up with an expression for the energy density that looks like this. And the overall energy density is not rapidly oscillating. It's evolution. So its amplitude is controlled by this initial condition, and its evolution with time is controlled by f of t squared, which we know scales like a to the minus 3. So this oscillating classical field, oscillating around the base of its potential, behaves exactly like just pressureless cold matter from the perspective of cosmology. It has the same 1 over a cubed scaling in its energy density that you would expect from a matter component. So this is dark matter in the cosmological sense. It's matter and it's dark because its coupling to the standard model is very small. So this parameter that I've called theta naught is I said that was an initial condition, but it's an initial condition for the A tilde field. The potential looks like cos A tilde over FA. So it's convenient to normalize out, to divide out the factor of FA in this theta naught, then this angle, which here I am calling theta, this is a dimensionless angle and it can take any value between 0 and pi, so it has a limited range of possibilities. So if I look at how much initial energy density was stored in the field when it started oscillating, it's just determined entirely by the mass, by the coupling, which are related to each other, and by this initial angle theta squared. So the late time density, it's basically just set by this misalignment angle theta. So this tells you, this is the parameter that's telling you in this cosine potential, did I start at theta equals 0? Did I start at theta equals pi? Did I start at some point in between? That tells you how much energy density you have stored in the field at the start of oscillations. And then we know that that redshift's like 1 over a cubed, so the late time density is just set by when these oscillations start, plus this initial condition, how much time they've had to redshift. So that's broadly the misalignment mechanism. From an oscillating classical field, you can get the right scaling. If you pick the right initial condition and your other parameters are favorable, you can get the right relic density. We'll stick in some actual numbers and see what kind of couplings and masses you need for the axion to get the right relic density in a moment. We'll say for the QCD axion, there's an extra subtlety to this. So far I've been writing MA like it's a constant. but it's not a constant for the QCD axion because you'll recall the potential in the QCD axion case is determined by the pion mass and the pion coupling constant. The expression that I wrote, so what this means is that the axion only takes on its late time value of its mass and its potential once you pass through the QCD phase transition. Like prior to that, the pion is not one of the degrees of freedom in your theory. So, and the axion is effectively massless. So for the QCD axion, you have to do this calculation fairly carefully, taking into account how its mass turns on during the QCD phase transition. Before that, it's frozen. You just have the solution where the mass of the axion is 0 and A is, and the field value is fixed. Yeah?
Do we know the QCD phase transition physics well to do this?
There are calculations, like, I mean, so I don't, you can get an estimate. There are lattice calculations of this is the state of the art. The PDG has the particle data group has a review on axions where it lists various calculations for what the resulting axion abundance is. I'll show you what these numbers are, but I don't have a good sense of what the full theoretical uncertainties are coming out of the lattice calculation, for example. So it's, yeah, I mean, you can model it, but I don't know what the systematics are. That said, I mean, as you'll see, if it's just an error of like a few tenths of % or whatever, then that translates, if that just translates into changing theta by a few tenths of %, which is a completely arbitrary initial condition, then it's not a big deal. So yeah, you can get pretty strong predictions if you assume that the appropriate thing to do is to take some kind of RMS average over theta, and so in that case, even relatively small errors in the calculation might be somewhat important. But as I'll show you in a moment, in that case, there are larger sources of uncertainty. So yeah, so zero theta, we know it well enough to make an estimate. I don't know what the systematic uncertainties are, but I don't think that's actually the dominant source of uncertainty in this problem.
Not smaller than the astrophysical one.
Yeah.
So there's been a recent recalculation of the instant-on effects for Rupert ICP. I mean, they've gone as far as you can. And
okay.
Given that we don't know what this initial theta was.
Yeah.
Sorry, just this theta term, it doesn't look like an initial condition for the phase of the cosine. It looks more like an amplitude for the cosine. So how can you interpret it?
Okay, good. So there are two cosines here. There's the potential itself, which, if you recall back to last time, the potential had the potential had an argument of this term. So V equals a constant times this. Sorry, can you see? Yeah. So there's a potential of this term, and then. So once this potential is fixed, if I start out my axion at some point here, then it will start to oscillate back and forward in this, just like if you started a ball rolling on a hill, then it would roll back and forward in this valley. The expansion of the universe is acting as a frictional term which damps its oscillations over time and reduces the energy stored in that. So this oscillation has a time dependence where this isn't strictly, where there's an initial condition times f of t times cos mat. So two different cos terms here. So then the statement is, so I could substitute this a of t back into here, and then this divided by fa behaves like an angle. And so I can ask, what is the initial value of that angle? Does that make sense? Okay, good. Okay, so we now have so we can now try to predict the late time abundance of this, but with this dependence on theta. So there are two possibilities for how this might behave. So one question you might ask is the value of theta the same everywhere? Is it the same everywhere in our observable universe? And there are broadly two options for this. maybe theta was set prior to or early in inflation, when this angle theta is usually set by some underlying symmetry being broken. So if the angle theta was set prior to inflation, then we would live in a patch with some value of theta, and inflation would expand the size of that patch to cover our whole currently observable universe and then some. So in that case, with that early setting, when the axion starts to exist early on, you would expect that theta is the same everywhere that we can see, and its value is just determined by this random draw in the very early universe. So it could in principle take any value in the range between 0 and pi. You might worry that it's a bit fine-tuned if you need an extremely small value or a value that is very close to pi, but in principle it can take any value and it's just an initial condition. The other possibility is that this symmetry isn't broken until after inflation. Theta is set, and so different patches of the universe after inflation pick up different theta values. Now, after inflation, over time and through the epoch of dark energy domination, we see more of the universe as time goes on. Patches that were causally separated at early times become causally connected as time goes forward. So in that case, our observable volume today should be an average over many different theta patches. So in this case, the axion density in our universe, we don't need to specify just one value of theta. We should be taking some kind of principal average. In this case, there are additional subtleties where you can produce domain walls between regions that have different values of the axion field. And you can also form axion strings, which, again, topological defects, and these can subsequently decay. In general, after the QCD phase transition will decay, and so that can produce additional dark matter axion energy density beyond what's stored in the smooth field. So the calculation in both of these cases are non-trivial, but in the second case, it requires moderately complicated simulations because you also have to simulate the formation of this string network and domain walls. So the first case, you still need to worry about what's going on during the QCD phase transition. But the PDG review on axions says that in this case, when you do the calculation carefully, this is what you get for the relic density. So you get the correct relic density times a theta squared parameter. You get a correct relic for a theta of 1, you get the correct relic density at an axion mass of about 6 micro eV. And then there's a scaling roughly as 1 power of mass as you move away from that. Lighter axions are more weakly coupled and give a higher relic abundance in general. So if I want to go to really light dark matter, if I wanted to put in an MA of 10 to the minus 21 EV here, like the limit from the wavelength, then I would need theta to be extremely tiny to cancel out the many orders of magnitude. Now, so this could mean that I have just replaced my fine-tuning, that I have in some ways like replaced my fine-tuning problem of the strong CP problem with a different fine-tuning problem, that now I want theta to be 10 to the minus 10. Now, when people argue for that, often an argument they make is that maybe you can make some kind of anthropic argument that if you had 10 to the 10 times too much dark matter, the universe would look extremely different. I'm not a huge fan of anthropic arguments because they often lack explanatory power, but changing the amount of dark matter is one of the things that would change how galaxies form in the universe. So it's not completely crazy. So yeah, so in this case, in this uniform theta case, your abundance is essentially just set by the initial condition. You can dial it over a fairly wide range. You can't dial it up arbitrarily because theta squared can't be much larger than order 10. So if you want the QCD axion to be 100% of the dark matter, this pushes you again into a range where the mass is about 0.1 milli eV or less in this case. But you could go down to very low masses provided that you're willing to have the correct initial condition to get the right relic density. If we look at the other case where theta gets effectively averaged over the patches, there are some very recent simulations following on from earlier simulations, which find that when theta is set after inflation and you take this average, the axion dark matter density is just given by this result. They wrote it in terms of FA instead of MA, but this corresponds to a QCD axion mass of about 25 micro EV. So this, so this sort of tells you, okay, if theta is going to be order 1 to pi in this range, you should be looking at masses of around between 10 and 100 micro eV to get the right relic density. Now, these simulations, they do find that the contribution from the axion string decay is pretty small. There's been some work by other authors. This is one paper that's an example that argues that it could be easy to miss a fairly large contribution from axion string decay by changing our assumptions a little bit. So like, if you had an additional contribution to the relic density, then that means that you could have a higher QCD axion mass. So you'd have a smaller abundance from what's just stored in the coherent field, and then you get an extra contribution from axion string decay. So modulo those caveats, you should be thinking of sort of a maximum mass for the QCD axion in this tens to hundreds of micro eV regime. Okay, so that was basically what I wanted to say about the cosmology. Are there questions about that at this point? Yeah?
The problem of domain was that they tend to dominate the energy density.
Yeah.
Is it relative?
So that's a good question. So the question was, so domain walls, their energy density redshifts in a way that causes them to dominate at late times. It's like, so the domain walls in this case would decay at the QCD phase transition. So long as they don't dominate before, like they can decay into axions. So long as you don't dominate once the axion has a mass. So long as you don't dominate before then I think it's okay. But yeah, I don't actually have a good handle on how that much will constrain the parameter space, although the energy density stored in these simulations at least, with their setup, they were finding that the topological defects don't give much of a contribution to the energy density. So I would expect that in that case it's not a big deal, but I don't have a very good handle on how sensitive that is to these assumptions. I haven't done those simulations myself. It's a good question though.
If there is a magnetic field, so there will be conversion from axion to photons.
Yeah.
Non-resonant and resonant. So do you have some comments on this?
Yeah, so let's talk about axion searches. Then. Yeah, okay, so axion searches, in the US we had a report, we had a big white paper called Cosmic Visions 2017 a couple of years ago, which lays out a lot of ideas for axion searches, so that's a good place to start reading. There are also a number of good review talks around, in particular the one that Benjamin Safdie gave at the Identification of Dark Matter conference last year is pretty up to date, and I'm going to be stealing some of his plots for this. So, but the basic principle behind the vast majority of axion searches is that in the presence of a magnetic field, the axion can convert into a photon, or vice versa. This comes from just in the same way that the axion couples to the gluon field strength. There is generically, for the axion, a coupling that looks just like this, except that you replace the gluon field strength with the photon field strength. So then this looks like a E dot B over FA coupling. So the exact coefficient out the front of this is model dependent. It depends on exactly how your axion physics is set up. But yeah, there's a range of benchmark models that people use, but there's usually an order 1 coefficient there. So the presence of this process means that if you've got a magnetic field, photons can convert into axions, and then back. This can allow a few different things. This means that if you have a region that photons usually couldn't pass through, they would usually get absorbed. They can convert into the very weakly interacting axion, go through that region, and then turn back into a photon on the other side. This means that you can get propagation through both like physical regions on Earth and across distances in the universe that would otherwise be impossible. So that's, you take a photon, you turn it into an axion. You can also have the reverse of this process where the axion dark matter converts into a photon or into effectively a modification of Maxwell's equations, a modified electromagnetic field. And that's another way to search for them. So some of these searches are really just testing for the presence of axions, whether or not they're dark matter. The other one is specifically looking to convert the dark matter axions into visible photons. Axions can also do the QCD axion can also do other interesting things. It can induce nuclear electron dipole moments, which you can look for at the Casper experiment, looks for those. During Big Bang nucleosynthesis, the presence of an axion that hasn't oscillated down to its minimum can slightly change the proton-neutron mass splitting, which changes the decay lifetime of the neutron and hence changes the amount of light elements coming out of nucleosynthesis. So there are some constraints from that. So if you're talking about the QCD axion specifically, you can have interesting QCD effects. Often when we talk about axion-like particles, we assume that there's some kind of vertex of this type, and then most of the other axion searches go through for models of that type. So this is a not exhaustive list of axion probes that people have thought about. So what are regions that are usually opaque to photons? Well, if you have very high energy photons traveling through the universe, then if they're high enough energy that they can pair produce on the background light, then usually that's what happens. The pair production rate is pretty fast. The photons get absorbed into production of electron and positron pairs. As a consequence, we don't expect to see any gamma rays coming from beyond our galaxy above a certain energy. So if you do start seeing gamma rays coming from very distant sources, that could potentially be a handle on the axions. The downside of this is that it requires knowing what the background photon spectrum looks like pretty well, because if there are somewhat fewer high energy background photons than you thought there were, then maybe that gamma ray that you saw wouldn't have been above the threshold for pair production after all. But so Fermi and Hess and Veritas and other gamma ray telescopes have various axion searches using this strategy. You can do light shining through a wall experiments, which is what it sounds like. You are looking to have some small fraction of a beam convert into axions and reconvert on the other side, thus allowing the light to pass through a region that it would not otherwise be able to. In the stellar cooling context, from stars can be pretty opaque to photons. If those photons can convert into axions, they can escape the star when they otherwise wouldn't be able to, allowing that to be a source of cooling. So if you see more or less cooling, you can use that to set constraints on the photon-axion conversion rate. If you have photons that are not fully absorbed, but when they pass through the magnetic fields of galaxy clusters, photons of the right energies to convert into axions in those clusters could convert, leading to spectral features in the gamma ray spectrum that you see having shone through the galaxy cluster. I'm going to post these slides online, so don't worry necessarily about noting down all the archive numbers. So then there's the turn cosmological axions into something that you can detect. The classic here is the ADMX experiment, which I'll say a little more about. Next slide. There also the experiment CAST uses the magnetic field of the sun, says, okay, maybe in that magnetic field incoming axions could convert into X-rays, and we can look for those X-rays. The next generation version of this is called IAXO, and is going to, as you'll see in a moment, is going to push the constraints down pretty far. There's been a lot of work just in the last year or so about looking for X-ray and radio emission from other stars. So if you have white dwarfs or neutron stars, those can have pretty strong magnetic fields, especially neutron stars, and just axion dark matter flowing through could convert into photons, could resonantly convert into photons when the magnetic field hits the right value. And that gives you, that could give you resonant features in the X-ray and radio spectra. There's an experiment called Abracadabra at MIT. The first prototype has been built and released results at the end of last year. They're basically looking for modifications to Maxwell's equations. A term like this is effectively an extra small term in Maxwell's equations. So you can look for the presence of the dark matter axions inducing a very small electric current that you can search for. MADMAX is a different kind of experiment. It's looking at conversion of axion into photons at the interface between different dielectric materials. And read the references. There are a lot of these experiments. ADMX, so I mentioned that ADMX will actually get a plot out of this ideas. So the idea here is that you build a resonant microwave cavity, and then you measure the output power from the cavity. The axion photon conversion will occur resonantly if the frequency of the B field matches with the axion energy. So you vary the cavity frequency very slowly, and you look for the power from the cavity to spike upwards due to the axion photon conversion. So this is sort of the picture of what they're looking for as they vary the frequency of the cavity and look at the power. They're looking for a narrow, a narrow spike. So if you detected a spike like this, you not only would have found the axion, you also would have measured its mass pretty precisely. They are doing an upgrade, well have been doing an upgrade at the moment. They put out some results last year, which was testing the QCD axion in a very narrow mass range between about 2.66 and 2.81 micro eV. So that'll basically just be a line on the plots I'm about to show you. This is kind of a flagship axion search experiment, but sort of the downside is that they need to scan, because the frequency resonance is rather narrow, they need to scan a lot of different frequencies to be able to cover a broad range, and that takes time. But if they do find something, they will also have measured the axion mass really precisely. So this is taken from Ben Safdie's talk late last year. So this was an estimate of what the current axion limits are. So this is now in the space of the axion coupling. This is what we've been calling before 1 over FA. So this is actually G A gamma gamma, which is essentially the coefficient of this, which is the coefficient of this AE dot B term. So we expect it to scale as 1 over FA times some coefficient. So this yellow band here is what we'd expect from the QCD axion. These red lines are two different models for exactly what those order 1 coefficients are in front of this coupling. You can see the expected as the mass goes down, the coupling goes down as well. And so then these colored regions are ruled out by different strategies. So these helioscopes looking for axion conversion to X-rays in the sun largely just kill this high coupling region. These gray regions here, the lowest of these is coming from supernova bounds. The gray regions here are coming from the tests that I mentioned, looking for high energy gamma rays and seeing if they can converting to axions on the way to us. And then these green regions come from haloscopes like ADMX. Now, this plot only goes down to 10 to the minus 10 EV axions. If I go down to significantly lower masses, although that's a bit scroll. Okay, this is 10 to the minus 15 at the base of this plot. This is 10 to the minus 11 EV. This is 10 to the minus 7 EV. So down at this range, the abracadabra experiment has so these are 3 different versions of the abracadabra experiment, where this is the 10 centimeter version that is probably plausible to build in the near future, and these are the increasingly ambitious far future versions. So and these are getting down to couplings at this is a 10 to the minus 20 1 over GeV coupling. So this would be probing pretty high scales. So this is a status report. These are all forecasts. This yellow line again is the QCD axion band. If we look at the projected limits for the heavier axions on this upper plot, so basically the projection is that the successor to the Helios to cast IAXO is going to keep coming down from above, constraining these high coupling regions, and the haloscope experiments like ADMX, but also MADMAX, another one called Haystack that I didn't mention, are going to fill in this space, getting down into the QCD axion region and expanding the mass reach. So these the abracadabra would start cutting into this region and down here at lower masses. So that's broadly where we are. There's a wide range of experimental strategies. I've just given you a brief survey. Ask me for more references if you need to see more. Okay, so now I want to switch to a completely different topic. So does anyone have any last questions on axions before I move on? Yeah?
Can you get back to the previous slide? Just one. So why there is a gap in Fermi?
That's a good question. There was a few years ago some hints of like high energy photons that people wanted to claim as possible evidence of axions. So it's possible that those is like sculpting a region in Fermi that is not as disfavored. But I don't actually know. Let me look it up and get back to you later. I don't know what sculpts that band. It's a good question. In Fermi, the issue was basically, so there was a claim that you were seeing higher energy photons than you would expect, and then they recalculated the infrared background light spectrum. You could imagine that maybe there's 2 sigma evidence for axions, and that hollows out some bit, but it's a little bit surprising that it's so far inside the region. So I don't know exactly what's going on, but it's a good question. Okay, so now let me move away from axions and say, okay, so I've just told you a bunch of ways that we can look for axions on Earth and in astrophysical and cosmological contexts. So now, and for the rest of my time, I want to switch over to other sets of searches that we can do for other dark matter models, moving more back towards the higher mass end of the spectrum of possibilities. What I've told you about axions covers a lot of the range of very light, low mass dark matter. If you have an interaction like this, a lot of these searches are quite generalizable to other low mass dark matter candidates. So now I'm going to take a jump up the mass scale and ask, okay, how can we look for processes that would be sensitive to the kind of thermal dark matter candidates that we talked about earlier? So these are the classic search strategies of, on one hand, of direct detection, colliders, collider searches, and indirect detection, which my colleague Jesse Thaler likes to refer to as shake it, break it, and make it, respectively. So first, if I were to ask just generally what kind of interaction structures can dark matter have with the standard model, so okay, there's that structure, there's axions, but more generally, if I'm thinking about dark matter as a particle, not as a wave field, I might say, right, well, broadly speaking, I said before I could have annihilation, which is 2 dark matter particles go in, some standard model particles go out, but I could also imagine, so this is the break it, but I could also imagine rotating this diagram and saying, well, I could have a dark matter particle comes in and bounces off a standard model particle. If this happens, there's no number change, there's no conversion of mass energy into visible energy, but I can look for the recoil of this X particle. Or I could turn the diagram around again and say, well, what if I have 2 standard model particles go in and 2 dark matter particles go out? If the dark matter is heavy, this is going to require the standard model particles to go to be moving pretty fast, so we can look for this kind of search in collider experiments. So this is make it. So I'm going to begin by talking about this generic structure where dark matter particles bounce off standard model particles, and we want to look for a scattering process between the two. So the basics of this strategy, which is called direct detection, are I want a large volume of standard model stuff because these scatterings are rare, so I want as many X targets as I possibly can. I want to sensibly instrument that volume because I want to be able to see individual target particles jumping, and as we'll see in a moment, those recoils can be pretty small, so we need the detectors to be pretty sensitive. We also need to reduce background, so these experiments are typically buried deep underground. Ideally, this reduces the backgrounds you have to worry about to neutrinos or dark matter, and at present, the neutrino background that we expect from supernovae and for the sun is too faint to be seen, but we're starting to move towards that neutrino floor where that will become a background. The 0th order result of these scattering experiments is that if you constrain the scattering cross-section between WIMPs and nucleons, you can set a limit that it's at its strongest for dark matter masses of about 30 GeV, and with a cross-section of about 4 times 10 to the minus 47 square centimeters. Now, this is a very small cross-section. If you were to do the kind of parametric estimate that we did before for the annihilation cross-section that I told you about corresponds to sigma v of about 10 to the minus 26 centimeters cubed per second. It's a bit different because that was a scattering cross-section. This was annihilation, and the other one was an annihilation cross-section. They have different scalings with velocity, but it's generally broadly true that if you've got a tree-level exchange of a Z boson or even a Higgs boson around this mass range, the cross-section that you expect is well above these lines. So this puts some reasonably tight constraints on how dark matter can couple to the standard model. Okay, so so on this I said, okay, I plot a WIMP nucleon cross-section. What do I actually mean by that? Because that's not actually what we see. So our observable is going to be the rate of scatters as a function of the recoil energy of the scatter. So the first thing that I can do here is just like work out the classical kinematics of the problem. If I'm talking about scattering of protons or neutrons, I can really treat this as like just a classical billiard balls problem. So let's work this out in the lab frame. To begin with, we just write down energy and momentum conservation, say that the dark matter particle, indicated in light blue here, has initial velocity of v. Afterwards, it has a velocity of v prime and scatters off at an angle theta prime. The thing that we can actually see is the recoil at an angle theta of the nucleus. So we write down the energy momentum equations, we do manipulations that I'm sure you've all done many times, and that algebra gets us to a recoil energy expressed in terms of the scattering angle that looks like this, where mu here is the reduced mass of the system between the target and the dark matter. So this result really only depends on the kinematics of the collision. If you've got a collision that isn't elastic, so there can be a non-trivial energy transfer, then you need to modify this, but otherwise this is pretty general. So there are a couple of things that you learn from this. So the recoil energy can be 0 if your theta is, if your scattering angle is sufficiently large. But, and it hits a maximum value that is 2 mu squared v squared over mn. So particles scattering at a given velocity produce a band of possible recoil energies. So that means another way to say that is that if I'm looking at a given recoil energy, only dark matter particles with velocities higher than a certain minimum value can possibly contribute. So we can do some quick estimates for what kind of recoil energies we should see here. If we take the target nucleus to be about 10 to 100 GeV, so it has 10 to 100 protons or neutrons, and the dark matter is a similar mass or heavier, then we can take the reduced mass to be just the mass of the target nucleus. The velocity dispersion of dark matter in the Milky Way halo is about 10 to the minus 3 times the speed of light. It's a few hundred kilometers per second. That's set by the galactic gravitational potential. It's what we measure with when we look at rotation curves. So then the typical recoil energies should be in the range of about 10 to the minus 6 times the mass of your target, which for a typical atomic nucleus is going to be about 10 to 100 keV. And that's for heavy dark matter. So you need your detectors to be able to see 10 to 100 keV nuclear recoils. Now, if the dark matter is significantly lighter than the nucleus, the situation gets much worse, because then the reduced mass is set by the dark matter mass, not the target mass. So relative to this calculation then, the recoil energy is suppressed by the ratio of the dark matter mass to the target mass squared. So then maybe instead of, so if you're looking, say, for 1 GeV dark matter, then instead of your recoil energy being 100 keV, it's only going to be 0.01 keV. So you'll see on this previous plot that the limit gets bad very quickly as you go to sufficiently low masses. That's basically this argument. As soon as the dark matter is significantly lighter than your target nucleus, you start to lose sensitivity very fast. So detecting light dark matter this way requires light targets and very low energy thresholds. But you can also do other tricks like looking for the scattering off electrons, which are lighter, or looking for the absorption of very light dark matter onto targets or other things that are not elastic scattering. But this is why elastic scattering on nuclei is a hard way to look for light dark matter. So if we want to understand, if we want to predict the spectrum, what we need to know is the amplitude for scattering of the dark matter on the individual nucleons. So for that, there's a particle physics component, which is how does the dark matter couple to the quarks and gluons? And there's a nuclear physics component, which is what is the quark and gluon content of the nucleus, and how do I combine these results? Once we've got the amplitude for scattering on individual nucleons, what we can actually observe is the amplitude for scattering on the nucleus. Well, in fact, that's not even really what we observe, but this is one of the steps that we need to do. So there's a particle physics question here, which is, well, what does the amplitude depend on? What are the signs and sizes of couplings to the different nucleons? Is that, for example, does the amplitude depend on the spin of the nucleon you're looking at? If it does, then contributions from nucleons with opposite spins can cancel each other out. Does it couple differently to protons and neutrons, for example? And then there's a nuclear physics step, which is what we call the nuclear form factor, which essentially accounts for the finite size of the nucleus. Then, once we've got this amplitude, we still need to go to the actual scattering rate, which is what we really see. And so then there's an astrophysical component, which is the number density of dark matter in this region and how fast it's moving. So the way that this is typically done, which is not going to be correct for all models, and actually a lot of variations on direct detection modeling is basically just to relax some of the standard assumptions and then see what happens. But the standard set of assumptions is to say, let's assume that the scattering is a contact interaction, and we can parameterize it completely by just a single coupling to the neutrons of the dark matter and a single coupling of the protons to the dark matter. We typically take these to be just constants, which don't depend on the velocity, or the level of momentum transfer, or the scattering angle between the particles, or anything like that. It's also usually further assumed in these limit plots that Fn, well, it's often further assumed that Fn is equal to Fp, but that's not an essential assumption. We then typically consider two cases where the interactions either depend on their sign is determined by the spin of the target nucleons, in which case the amplitudes from paired nucleons cancel exactly and the overall rate scales as the net spin squared of the nucleus, or you assume that these amplitudes are spin independent and add perfectly coherently. So in that case, spin independent bounds tend to be much stronger because of this coherence, you get a signal that scales like the atomic mass of the target squared. The form factor. This determines the momentum dependence of the interaction just due to the finite size of the nucleus. What's typically assumed is just a simple parameterization, which is called the Helm form factor. I'll say a little bit more about that in a sec. The dark matter velocity distribution, we typically just assume a Maxwellian velocity distribution for the halo. So basically just a Gaussian for the velocity distribution in the halo. So, as I said before, a lot of non-standard models just work by changing one or more of these assumptions. As you change these assumptions around, they can often modify the constraints by a non-negligible amount, especially if you're close to that low energy turn up in the constraints. So this is, so I'll just do this briefly. This is the analytic prescription for the Helm form factor. So essentially this just multiplies the rate that you're seeing. So this depends on, this is a function of the momentum transfer between the nuclei. It's an important effect for momentum transfers corresponding to scales of about a femtometer or smaller, which is a momentum, so for V of, which is a momentum for the incoming particle greater than about 100 MeV. For V of 10 to the minus 3, this is only really relevant for dark matter that's heavy, like above 100 GeV. So if you care mostly about the 10 GeV range, this probably isn't a huge effect. But as you go to heavier dark matter, it makes a difference. In the standard calculation, I'll just get through this and then so this is again just elastic hard sphere scattering. You could do it back in your first year mechanics class. So now we'll switch into the center of mass frame. Why do we switch into the center of mass frame? Because we're going to make some assumptions about the cross section not depending on any angles. The center of mass frame. So in the center of mass frame, we can again do the kinematics of the collision. We can write down the momentum transfer in this frame, which is the 3 momentum transfer is q squared is just this result. It's again set by the relative velocity of the particles, the reduced mass of the system, and the scattering angle. So we already computed the momentum transfer in the lab frame. Everything's non-relativistic here. This is Galilean physics. The transformations between frames are pretty simple. So this lets us write the lab frame recoil energy, which is the actual observable that we can look at in terms of the center of mass frame scattering angle, and just write it like this. That lets us write down the spectrum of events at a given recoil energy, just in terms of what is your cross section for scattering at a given center of mass scattering angle, which looks like this. So now we've written the rate, so now we've converted the rate in terms of the observable recoil energy that we see into the scattering, into a dependence on the scattering angle in the COM frame. So then we now assume, let's assume this should be spin independent, sorry for the typo, let's assume spin independent scattering, so contributions from different nuclei add coherently. So then we're just assuming that the overall amplitude for scattering on the nucleus is this form factor, which describes the finite size of the nucleus, multiplied by z, so the number of protons times the amplitude for scattering on protons, plus the number of neutrons times the amplitude for scattering on neutrons. Then we can take this matrix element, we can convert that into the cross section in the center of momentum frame. This is just the usual result that you do in any QFT class. And the non-relativistic limit. the conversion from the cross-section to the rate. So this depends on the number of target nuclei that you have, the number of dark matter particles that you have, and their relative velocity. And if we then assume that there's no dependence on the angle phi in the center of mass frame, we previously had dr by der in terms of the differential cross-section as a function of theta. We assume there's no phi dependence, then we can write that just in terms of this matrix element. And so what we end up in the end, and I have a summary of this coming up which splits it up in a sensible way. This is our observable, this is our rate of recoils as a function of recoil energy. We can just write it, you see we have the form factor coming into play. This describes the particle physics of how the dark matter particles scatter on individual protons or individual neutrons. The fact that there's a plus sign here and all this adds coherently is telling you that the scattering is assumed to be spin independent and to add coherently. And then these factors tell you about the properties of the target, the properties of the dark matter, there's an MChi here, and the VREL and the dark matter cosmological density are described in the astrophysics. Okay. So, but what's actually plotted on these limit plots is not dr by der. It's this effective one nucleon scattering cross-section. So this essentially takes the scattering cross-section of the whole nucleus, evaluated at q equals 0. So again, that means that we switch off the form factor effect and rescale by the ratio of the reduced mass scattering off the whole nucleus versus just the reduced mass you would have if the dark matter was scattering off one nucleon, and as well as the number of nucleons in the number of nucleons available, which is the 1 over a squared factor. So this quantity, defined in this way, is the actual quantity that's bounded on those limit plots. The reason that we write it in this way is so that we can do comparisons between different experiments, but those comparisons depend on all the assumptions that I just made about the Helm form factor, about the velocity distribution, so keep this in mind. So we do some rearrangement, we do some redefinitions. We can then rewrite so we've then captured the particle physics into this sigma chi n factor. We can write our observable in this form. So we have our sigma chi n is characterizing the particle physics. We can write the sigma chi n in terms of these underlying matrix elements in this form. And this allows us to do a factorization of the observed rate into a particle physics term, which is characterized by the single nucleon cross-section, information about the target, information about the astrophysics, and the nuclear physics captured by this form factor. So this is kind of the master equation at the end. Now, this is written still in terms of just one single VREL. So this assumes that we know the incoming velocity of the dark matter particle. In reality, of course, we don't know this. The dark matter has a distribution of velocities. So we need to integrate over the velocity distribution. So the final answer, the final observable, gets factorized in this way. We have a dependence on the target properties, on how many nucleons you have, on the mass of the mass of a nucleon, on the number of targets, on the form factor. So like I said, is usually assumed to be the Helm form factor. We have a dependence on the dark matter properties, on the scattering cross-section, which is what's plotted, on the dark matter mass, on the reduced mass between the dark matter and a single nucleon. And then we have this astrophysical factor, which scales as 1 power of the local dark matter density and depends on this integral of 1 over v times the dark matter velocity distribution. So these are all the assumptions so this is what's actually plotted. If you know everything else, you can convert that into the observable that you would actually expect to see in an experiment. Okay, so I think that we should take a break at the moment, but so this is sort of the master equation for direct detection. We'll start next time and I'll show you where the current results are and where we're going. Thanks very much.